Hi everyone, so today we are going to talk about multi-factor ANOVA. In last lecture, we learned about ANOVA in the two-factor scenario, and we learned about the basics, the intuitions about the ANOVA test and an F test for comparing two different kinds of variances and these equations. So let's start with the example again. So about the dart throwing and how accurately can you throw a dart is the question, and it may depend on which hand you use and how far from the target you are. So there are two factors, and one is the distance and another is hand. So left to right and far, middle, near. The question is, how can we measure the effect of each variable? So this is the two-factor ANOVA model. So previously we showed Yij can be expressed like this, the gray mean plus tau j plus the epsilon. This is residual, treatment effects, and gray mean. So now we have two factors, hand and distance, and the equation should be changed. And we have one more factor. Previously we had ij, but now ijk. And j and k are two different factors. So I is ith observation, and j is level j of vector A. In this case, right and left hand. And k is level k of vector B. So far, middle, close for distance. And tau j and gamma k is the difference between the mean response of that treatment from the gram mean. So in the example case, tau is hand effect and gamma is distance effect. And null hypothesis for the test will be tau 1 equals tau 2 and gamma 1 equals gamma 2 and 3. And this is the example ANOVA table for that. This is really same with the ANOVA table from the previous lecture that had one factor, but this time we have two factors. But I will explain you the details of how this two-factor ANOVA works. So here I'm giving you another example. So tennis balls bounce with the different brands and temperature. So there could be some different brands. So standard brands is a little cheap, but standard, and premium is a good, like really expensive brand. And there could be temperature, freezer, fridge, room. So freezer, 냉동실, and 냉장실, and room temperature. And we can measure the bounce height for each temperature. So side by side box plots for each vector can be expressed like this, and this is effect, bounce, and premium and standard brands, and this is the bounce and room, fridge, and freezer. And this plot can be expressed like this, room, fridge, freezer, and brand, standard. So similar to previous lecture, we can decompose this Yijk into multiple different components. So one is gram mean, and another is brand effect, and temperature effect, and error. So like this. And this should be same, because the left side and right side should be same, because this should be cancelled out, and this should be cancelled out, cancelled out, and cancelled out. So it should be same. And this is the observation, and this is gram mean. And when we subtract the gram mean from this Yj bar, this should be 1.2, and this is a standard group, mean. So subtract gram mean from that. And temperature effect is the column, so Yk bar, and we can subtract the gram mean from that. And error is going to be Yijk minus the brand effect, so group mean for the brand and group mean for the standard. Because we are subtracting 2 times of gram mean, we just add the gram mean back to the value. Sum of squares of all these values, the brand effect, that is treatment sum of square, but treatment 1. Similarly, we can do that for treatment 2. So sum of the squares of all these values, and sum of squares of all these error value, and that is the sum of square of error. So this observation should be same to the summation of all these values. With just simple plot of the data, we really cannot easily see the effects of one factor only. Therefore, we need some kind of partial box plot. So plot the residuals for each level of the other fact. For example, so in the previous equation, this was the residuals, but we can remove one factor here, and that is this. So removing only the j factor is going to be partial box plot for k. So this is the partial box plot after removing, for example, the temperature effect, and then we can see the effects of hand. So this is actually raw data, and this is adjusted accuracy. So you can see after removing the effects of the other factor. So this is the partial plot for distance. So after removing the hand effect. So there is one additional really important concept. So that is additivity versus interaction. So when we say yijk equals grand mean plus hand, distance, and error, there is no interaction. So this model really assumes that the effects of two factor levels are additive. So we can just add the two effects of the two factor and get the total value. But there could be interaction. The effects of one factor could be changed depending on the other factor. That is the interaction. So when the effects of one factor change for different levels of another factor, to know this additivity versus interaction, we need to draw an interaction plot. So interaction plot is plot the averages of the observations at each level of the factors, like this. So each dot is the each level, the mean of the each level of the factors. So here blue line is hand left, and red line is right, and this is far, middle, and near. So if the plots are parallel, that means the data have additive effect. So this is additive enough condition. And if they are not parallel, it is the evidence that there is interaction. So these two lines are really perfectly parallel, but these are not. So we can highlight that using this type of plot. So interaction plot for the first example again, dart drawing. So from the middle to far, there was a large effect of hand. So for example, if that was right, there is not much difference. But if the hand is left, the difference between far and middle is huge. So the effects of the distance depends on the level of hands. We should include one additional term for that. Omega jk is that, and we call it interaction term. And df, degrees of freedom for interaction, is degrees of freedom for j times multiplied by degrees of freedom of k. So here, the distance and hand, and we have one additional term, distance times hand, and as you can see, the df is this multiplied by this. I'm going to tell you how to calculate this sum of square. So this was the ANOVA table without the interaction term, so it's a little bit different. So this is what we saw before, the brand effect and temperature effect, but we have one additional term, yjk bar minus yj minus yk bar plus y, the grand mean. So previously, the error was ijk minus this, but we now replace this with y bar jk, and then that is interaction term. And then residual changes into this. So yijk minus yjk bar. So residual is changed a little bit, but the important thing here is the interaction term. And sum of square of this value is the treatment sum of square for the interaction. So this tells you that y bar jk is the mean of this each level. So premium and room and premium and fridge, premium and freezer, and so on. So this area, and minus, subtract that, subtract yj bar from this each cell, yj bar, and yk bar from this, and plus grand mean. So that is how to calculate this. But we want to know what that means. What does interaction term mean? So let's say this is the yk bar, exact same group mean for k, but there could be low interaction case and there could be high interaction case. This is a parallel, this is not parallel and cross each other, and this dot is yj bar, so for one level, and this is for one level for j factor and k factor, and that the mean of that. And yjk bar minus yk bar for this level is this, and subtract yj bar is this, right? So we are thinking about only this level, this part. And for the other level of k factor is yjk bar minus yk, this and that. And let's think about this dot as well. This level, this j level and k. Ykj bar minus yk bar becomes really large, right? Because we need to subtract this from this. And this also became big, right? Bigger than this. And this is kind of similar, but this becomes really big. And similar thing has to happen for this level of J factor. Okay, so we are going to do the step-by-step example of the ANOVA test. So let's say we have the GPA data of 4 different groups of the students. There are 2 factors, gender and varsity, and 2 levels for each factor. So male and female, and here athlete team or non-athletes. So there could be 3 null hypotheses. One is the effects of sex level, gender level is same. There is no effect. So the mean of male equals mean of female. And gamma k is the effect of varsity level k, and for athletes and non-athletes they should be same. That's the null hypothesis. And also the third null hypothesis is for interaction. Interaction term is 0. And we can draw the side-by-side partial plot. This is the effects of sex after removing the effects of varsity, and this is the effects of varsity after removing the effects of sex. So it appears that there is no difference in mean GPA between men and women after accounting for varsity status, but there may be a difference between varsity athletes and non-athletes after accounting for sex. We can check independence assumption with a randomization condition. So the study was based on the random sample of students, so it's quite okay. And also we need to check the additive enough condition to decide whether we need the interaction term or not. So here's the interaction plot of the means of each treatment condition, and the lines cross. So we need to add an interaction term to the model and fit the two-way ANOVA with the interaction. So interaction. After that, we have a couple more conditions to check, but before that we need to run the analysis first. And then after that, we can draw residual plots after removing all the effects and check the similar variance condition. So we can see there's no thickening or thinning, so it's good. And also we can use these all residual values to check the nearly normal condition using the normal probability plot. So under these conditions, it is appropriate to interpret the f-tests with their p-values. So here, the error mean square, so this is the error mean square, 0.172 points, which means that the common error standard deviation, so total error standard deviation, is estimated to be square root of that is 0.415. Why we do the square root? To make the value have the same scale of the original data value, because it's a square root, and then we are going to have the value on the same scale. So that is nearly half a letter grade. So this is the amount of the grade that we cannot explain. The F ratio for the interaction term was 6.223 with a p-value 0.0134. Based on this, we can reject the null hypothesis of no interaction because there is interaction. So because of that, we have to be cautious in testing the main effects, but we'll examine the means further to understand the factor effects. So we can see the effects, and you can see that there is a varsity effect only. You can compare these two and these two, that is varsity effect, and these two and these two, compare these two are the sex effect. And there is no significant sex effect, so we can see only the varsity effect. So the main effect of varsity was significant, and varsity athletes have lower GPA by about a quarter of the GPA overall, but this effect is much greater for men than women. Okay, so that's it for today's lecture, and please don't forget to solve the quiz, and see you in the class. Bye.